Welcome, friends. I am so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quiet realm of stone that drifts between Mars and Jupiter, a place shaped by gentle forces and ancient rhythms. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The story folds seamlessly now into this slow expanse where the asteroid belt stretches like a faint river of matter, circling the sun in silence. Here nothing forms a continuous band and nothing glitters as it often does in imagined portrayals. Instead, isolated fragments drift through spacious darkness, each one separated by millions of kilometers, each one following its own quiet arithmetic of motion. A scientifically accepted truth settles gently into view. The asteroid belt contains only a tiny fraction of Earth's mass, far less than what would be needed to build even a single additional planet, a reminder of how the early solar system favored dispersal over gathering in this region. Sunlight touches the stones like a thin, patient brushstroke, revealing surfaces baked by radiation and scarred by impacts that occurred long before living eyes evolved to wonder about them. Some fragments are no larger than a grain of sand. Others, like Ceres or Vesta, have enough gravity to pull themselves into rounded forms, though even these worlds remain small and quiet compared to the planets they orbit alongside. A lesser-known detail drifts forward with the slow tenderness of a whispered note. The dust that permeates this region contains grains older than Earth itself, tiny calcium-aluminum inclusions that condensed in the newborn sun's first bursts of heat. They float here as though time itself needed a record, solving collision-born thermal cycles and the tug of planets to remain drifting witnesses to conditions that no longer exist anywhere else in the solar system. The mind lingers on one of the field's persistent mysteries, soft and unresolved: why this region never coalesced into a planet. Jupiter's overwhelming gravity prevented its scattering formative material and stirring the region into perpetual fragmentation. Yet the precise balance between disruption and survival remains subtly uncertain, shaped by complexities in orbital resonance and collisional evolution that continue to puzzle researchers. Only took a few billion years for this equilibrium to appear so calm, only required the restless shaping of a giant planet to hold everything in a state of perpetual almost formation, and only demanded countless collisions to produce such silence afterward. The stones move gently, their motions governed by the same laws that guide planets, yet expressed on smaller scales like a planetary system in miniature. Some tumble irregularly, releasing faint puffs of dust as micrometeorites strike their surfaces. Others glide in slow rotation, showing faces darkened by carbon-rich minerals. There is no tension, no anticipation, simply the quiet continuation of momentum, like a river that flows whether observed or forgotten. The imagery repeats softly: stone, light, distance, dust, each element returning as though to remind the listener that large events unfold over unimaginable spans, often leaving behind small, unassuming fragments that carry more truth than spectacle. In this region, the concept of now almost dissolves, replaced by processes that operate on scales so long that the present moment becomes just another grain floating among billions. A gentle modern analogy drifts in the belt feels like an old library where countless volumes have been scattered across the floor, each one containing a chapter from the solar system's earliest days, yet no single hand moves to reassemble them. The contemplative stillness deepens as the sunlight thins across distance. Every particle glows just enough to reveal its presence, and then fades back into the dark and interplay that repeats continuously as the belt circles the sun. It is a quiet irony that objects moving at tens of thousands of kilometers per hour appear utterly motionless when viewed against the scale of the void. Another irony that fragments born from violent impacts now drift as symbols of cosmic calm, and yet another that the region thought of as chaotic and crowded is in truth one of the emptiest expanses in near planetary space. These stones do not rush, do not collide often, do not reshape themselves quickly. They simply persist like an echo of early formation that never resolved into completion. Small shadows slide across their surfaces as they rotate the sun's faint pressure pushing lightly against them. The solar wind brushes away accumulated dust in microbursts, revealing mineral patterns shaped by thermal expansion and cooling that have repeated for billions of cycles. Over and over, the belt reminds the observing mind that most transformation in the universe occurs slowly, imperceptibly, through gentle repetition rather than decisive events. The narrative glides deeper into this thought, observing how even silence becomes a process. Here, dust drifts outward, under solar radiation pressure. Stones migrate slightly as gravitational influences shift and resonances create long, narrow corridors of instability that gradually empty themselves over eons. The emptiness itself is dynamic, shaped by rhythms that require no intervention. One might imagine that the belt has an edge or boundary, but its transitions blur softly into the surrounding space like shorelines erased by a rising tide. The inner edge is more a suggestion than a line where the orbits of Mars and the outermost fragments occasionally intersect the same gravitational harmonies. The outer edge dissolves gently toward Jupiter, where its gravitational influence becomes too strong for stable material to linger. The listener drifts through this region guided by the simple fact that everything here moves because gravity asks it to, yet nothing moves with any urgency. The contemplation settles on a final quiet observation. Though the belt is often cast as a realm of danger, its stones pose no threat unless nudged from their long-held orbits. And even then, the journey inward takes millions of years. The stones have time, and they give time, stretching it thin until every moment feels as spacious as the distance between one fragment and the next. In this stillness, the first section draws to a slow, continuous breath, holding the listener gently within a ring of ancient stone that circles the sun, without hurry, without intention, simply because it has always done so. The story drifts farther into the belt now, leaving behind the first impressions of scattered stone and moving toward the almost invisible dust that permeates this ancient region. Dust older than oceans, older than continents, older than the first traces of life that will one day rise on a distant blue world. The narration moves slowly, observing how each grain carries a history so long that it stretches past familiar measures of time back into the earliest heat of the solar system's formation. These grains are remnants of the protoplanetary disk, the same vast cloud of gas and dust that once swirled around the newborn sun like a luminous veil. A simple scientifically accepted fact settles softly. Many of these particles contain calcium-aluminum inclusions that formed during the first few tens of thousands of years after the sun ignited, making them some of the oldest solid materials known. They drift through the belt, not in clusters but as individuals, each grain a solitary traveller suspended in orbit shaped by billions of gravitational whispers. Sunlight strikes them briefly, scattering in faint arcs before fading into the surrounding darkness. The dust spreads in a thin, barely perceptible mist, yet it influences its environment with a quiet persistence. It absorbs. Sunlight warms gently and emits infrared radiation that slowly draws it inward toward the sun, through the pointing Robertson effect, a process so gradual it seems designed for contemplation. A lesser-known detail glides forward. Many of these grains contain pre-solar fragments, tiny bits of matter forged in stars that lived and died long before the sun came into existence. Embedded within these specks are isotopic fingerprints that reveal origins in ancient supernovae, and red giants suggesting that the asteroid belt harbours particles that remember stellar environments far beyond this system. They drift here not by choice but by the simple physics of inheritance remnants swept up during the formation of the solar system and preserved in this quiet corridor. A gentle mystery rises unresolved yet comforting in its persistence. How much of this dust truly reflects the earliest conditions of the solar system, and how much has been altered by countless collisions, solar heating cycles and chemical reactions with interplanetary plasma? Scientists understand broad patterns, but continue to encounter anomalies in isotope ratios, surprising mineral structures and chemical compositions that hint at processes not fully reconstructed. The belt keeps these secrets softly, as if the dust itself prefers to remain partially unread. Only took a moment of cosmic time for these grains to form, only took a few million years for them to spread across this region, and only took the quiet persistence of planetary orbits to keep them drifting here long after their parent environments vanished. The dust moves almost imperceptibly, guided by gentle forces. Micrometeorite impacts shatter larger fragments into clouds of fine particles. Thermal fractures on asteroid surfaces release new grains into the surrounding void. Solar wind ions erode exposed minerals, producing even finer powders that join the drifting haze. These processes unfold slowly without spectacle, like the steady weathering of stone on Earth, where centuries pass unnoticed by the rock itself. In the asteroid belt, erosion appears as expansion rather than decay, each collision adding complexity to the cloud of dust that circulates among the stones. The narration lingers on the texture of these grains. Some are rounded from repeated heating cycles. Others are jagged, their edges sharp enough to reflect rare glints of sunlight before being lost again in shadow. Their colours vary from deep carbon black to pale reflective silicates, forming a patchwork too Saturn to be seen except by instruments on passing spacecraft. If one could float here in stillness, the dust would appear as a faint shimmer when sunlight hits it from just the right angle, like a whisper of frost suspended in an endless twilight. Yet the belt remains largely dark and the shimmer is more imagined than visible, a reminder that much of the universe's beauty lies in what must be inferred rather than directly seen. Quiet irony emerges: the smallest objects in the belt hold the oldest histories. Another irony follows that these delicate grains outlast their massive parent bodies, and a third joins them. That dust, something often dismissed as trivial, becomes a chronicle of cosmic origins more enduring than planets themselves. The narrative glides through the gentle motion of these particles. Radiation pressure pushes some outward, while solar gravity and drag pull others inward. Jupiter's influence creates subtle oscillations in their orbits, stirring them but rarely capturing them. Over time, many drift so far inward that they spiral toward the sun and vanish in brief flashes of vaporization. These disappearances occur quietly unseen by any witness, and yet the process has shaped the solar system's history by continually removing fine material that might otherwise have grown into new bodies. The dust lives on borrowed time, though the timescale stretches far beyond any human frame of reference. A soft analogy slips in the dust, behaves like pages torn from an ancient book and scattered into a slow wind. Some eventually settle in distant places, others drift until they fade into nothing, but each carries traces of the original story. The contemplation deepens. Dust collisions create electric charges. Magnetic fields subtly influence paths. Plasma from the solar wind interacts with mineral surfaces in ways that alter chemical bonds. These processes are small yet cumulative, like the faint weathering of a shoreline, where each wave reshapes a grain of sand. The belt becomes not just a region of stone, but a laboratory where subtle interactions unfold endlessly, shaping matter into forms that reveal the long dialogue between sunlight motion and elemental composition. Time stretches here. Millions of years become like breaths, and billions become like the slow settling of sediment on the floor of an unseen ocean. The dust becomes part of a continuous cycle born from collisions, drifting through resonance pathways and ultimately being drawn inward or outward until the grain is lost. Yet the belt renews itself, producing new dust at a rate that balances its losses. This equilibrium keeps the region filled just enough to maintain its faint haze. The narrator observes the space between grains, a distance so large relative to their size that it holds more emptiness than substance. In this emptiness lies another quiet irony. The dust's influence is felt not because it is abundant, but because it is constant. Each grain interacts with sunlight, with magnetic fields, with gravity, contributing in small ways to the long-term evolution of the belt. Even Solence becomes populated here, filled with countless particles that drift without urgency. Slowly, the imagery returns to motifs already touched upon sunlight, thin as a breath dust holding memories of older stars, time stretched across orbits that never intersect. This repetition folds the listener deeper into the contemplative rhythm, allowing the mind to rest alongside matter that has rested for billions of years. The narration holds to its quiet purpose to observe, without dramatizing to reveal, without resolving to linger, without moving toward any climax. Nothing hurries, nothing concludes. The dust simply exists suspended between two planets in a region that invites stillness. The second section settles like the grains it describes, drifting into the gentle awareness that even the smallest fragments of the cosmos contribute to the vast and unending unfolding of space. The narration moves softly now into the governing quiet of gravity, the gentle force that shapes every motion within the asteroid belt. It is not a force that rushes or insists. Instead, it spreads through space as a steady presence, guiding each fragment with a touch so constant it becomes more like the memory of direction than a command. Gravity rules here with patience, forming pathways that extend across millions of kilometers, curving lightly around the sun and bending more steeply when the immense pull of Jupiter enters the scene. A simple accepted fact arrives without emphasis. The asteroid belt exists in its present form because Jupiter's gravity prevented planet formation, stirring early material and dispersing it before it could gather into a coherent world. The belt is a remnant of this early shaping, a place where gravitational harmonies produce order and disruption in equal measure. Light drifts across these orbits, revealing how even small differences in distance from Jupiter create changes in orbital periods that ripple outward over time. A lesser-known detail floats forward with soft clarity. Within the belt, many asteroids occupy narrow regions called mean motion resonances, where their orbital periods match simple ratios of Jupiter's. These resonances do not appear dramatic, they are quiet numerical relationships that unfold over centuries and millennia. Yet they guide the shifting architecture of the entire region. They can stabilize orbits, allowing certain stones to remain in place for billions of years, or they can destabilize them, slowly increasing eccentricity, till the asteroid drifts into a new path. These relationships are like musical intervals played so slowly that a single chord takes millions of years to resolve. A gentle mystery settles nearby, one that scientists still explore: the precise long-term stability of these resonances and how chaotic interactions propagate through them over astronomical time. Some resonances appear stable for hundreds of millions of years, but unstable over billions. Others appear chaotic, yet maintain structure far longer than models predict. The belt shows how complexity can emerge from simple laws when enough time is allowed, and how even well-understood physics can produce outcomes that resist full reconstruction. Only took the early solar system's brief turbulence to set these resonances in place. Only took Jupiter's enormous mass to keep them active across epochs, and only took a few billion years for their influence to carve recognizable patterns into the distribution of asteroids. The scene widens. Countless bodies follow elliptical paths, each orbit shaped not just by the sun's dominant gravity, but by the collective tug of thousands of neighbors. These tugs are tiny, often immeasurable on short timescales, yet over long intervals, their cumulative effects alter inclinations and longitudes of ascending nodes, gradually dispersing asteroid families or aligning them into new patterns. The belt behaves like a vast, slow-moving fluid whose currents are defined by gravity rather than motion through a medium. The fragments do not sense these currents, but they follow them nonetheless. The narration lingers on Jupiter's influence, which extends far beyond its physical boundaries. Its gravitational field reaches across the belt like a broad, gentle hand, shifting orbital energies with each encounter. Resonances such as the 3-to-1 or 5-to-2 create gaps, regions where asteroids are gradually removed, while others form pockets of stability where material remains untouched for eons. The Kirkwood Gaps, named after 19th century astronomer Daniel Kirkwood, are the most visible signs of this influence, appearing as distinct voids in the distribution of asteroid orbits. Yet these gaps are not empty in a dramatic way. They are simply less populated, shaped by the long-term migration of bodies toward orbits, where resonant interactions become gentle but cumulative forces of removal. A soft irony unfolds: the belt structure is not random but shaped by mathematical harmonies. Another irony follows: that these harmonies simultaneously create order and instability. And a third joins them: that the quietest regions, the gaps where nothing remains, are the clearest evidence of gravity's persistent voice. The contemplative gaze shifts now to the asteroids themselves as they move through these gravitational rhythms. Their orbital speeds vary with distance from the Sun, their paths shaped by both eccentricity and inclination. Some orbits tilt several degrees above or below the ecliptic, creating a subtle three-dimensional structure that resembles a thick, diffuse cloud rather than a flat band. Light moves across these trajectories as though brushing over a complex sculpture, revealing how each curve holds a unique balance of forces. This region is neither chaotic nor orderly, but something in between: a quiet, dynamic equilibrium where structures exist but change slowly, dissolved and rebuilt by gravitational interactions over millions of years. The narration continues without hurry, observing how secular resonances shift inclinations over time. These resonances occur when the precession of an asteroid's orbit matches that of a planet, especially Saturn, creating gentle but long-lasting tugs that alter the plane of motion. The shifts are subtle, so slow, they evade casual understanding, yet they shape the vertical thickness of the belt and produce faint patterns in orbit distribution that researchers continue to decode. A modern analogy drifts into view. The resonances behave like the slow bending of branches under steady winds, imperceptible in the moment, unmistakable over time. Jupiter's influence returns again, as it always must in this region. The giant planet's orbit has not always been fixed. In the early solar system, it migrated inward and later outward, a process described in the NICE model and related frameworks. These migrations, though largely complete billions of years ago, left lasting imprints on the belt, scattering some material outward, depleting other regions, and shaping the distribution of asteroid types across different distances from the Sun. The belt still carries these signatures like soft scars in orbital alignment that speak to events long past but not forgotten. The listener drifts deeper into contemplation as time stretches even further. Collisions occur, but rarely compared to the density often imagined. Most asteroids remain separated by enormous distances, influenced by gravity far more often than by impact. Gravitational encounters between asteroids are typically weak, yet over millions of interactions they produce measurable diffusion through orbital space. The belt evolves through these interactions, still responding to early forces while slowly adjusting to new ones. It exists in ongoing conversation with the planets, particularly Jupiter, whose presence both stabilizes and perturbs. A quiet fact lingers: gravity here is not simply a pull, but a sculptor shaping both the emptiness and the matter within it. Shadows drift across asteroid surfaces as the Sun rotates in slow arcs relative to them, heating one face and cooling the other, while their motion remains governed not by internal activity, but by the delicate balance of gravitational forces surrounding them. A gentle recognition forms everything in this region responds to gravity in its own way, from dust to massive bodies, yet the response is always calm, always gradual. Another soft irony emerges that the most powerful force shaping this region is also the least visible, that the belt's dynamic structure appears static on human timescales, and that planets, though distant, hold more authority over these stones than their own mass ever could. The section settles into its final contemplative breaths, recognizing how gravity binds the belt together while also preventing cohesion. It is a quiet governor, writing paths so old they resemble habit more than motion-shaping stones that continue orbiting long after their origins fade into geological memory. The belt exists because of gravity shaped by it, defined by it, and yet forever drifting in a state that feels both unfinished and complete. The narrative glides deeper into the architecture of the asteroid belt, settling now into the strange quiet of the Kirkwood gaps, those long, narrow spaces that appear not through absence alone, but through the slow mathematics of resonance. From a distance, they are invisible, mere statistical hollows in a distribution of orbital periods, yet when viewed through the lens of time, they reveal themselves as the soft fingerprints of Jupiter's distant gravity. Nothing dramatic happens here. No stones abruptly veer away, no collisions carve out the emptiness. Instead, the gaps emerge as the quiet consequence of orbital rhythms repeating over millions of years, slowly pulling asteroids out of unstable regions and guiding them elsewhere. A simple grounded fact settles at the center of this meditation. The Kirkwood gaps correspond to mean motion resonances, where an asteroid completes a specific number of orbits for every integer number of Jupiter's orbits. In these resonances, gravitational Nudges accumulate with patient consistency until the asteroid's path stretches or shifts enough to remove it from the region. The process does not hurry. It unfolds with the softness of erosion wearing down orbital stability the way wind shapes stone on Earth, not by force but by persistence. Light drifts across these gaps, though there is nothing tangible to illuminate. They exist as absences, openings, or are being sculpted not by what is present, but by what cannot remain. The belt flows around them like a river that has carved its own invisible channels, leaving behind shapes that can be felt only by tracing the orbits of countless fragments. A lesser-known detail drifts forward. Some resonances within the belt do not create gaps but cluster stable havens where asteroids linger, with surprising longevity. These are zones where gravitational harmonies produce calm rather than chaos, balancing subtle tugs in ways that prevent orbital drift. The contrast between resonant gaps and resonant sanctuaries forms a quiet duality, order and instability woven into the same mathematical structures expressed through different outcomes depending on the delicate interplay of orbital parameters. Yet mysteries remain gentle and unresolved. Despite centuries of study, the long-term evolution of resonances still holds uncertainties: how overlapping resonances produce chaotic diffusion, how secular interactions with Saturn alter the shape and depth of gaps, how collisional families migrate across them, and why certain resonances behave differently from theoretical models. The gaps whisper of these uncertainties, holding space not just in the belt, but in the understanding of those who study planetary dynamics. Only took a few million years for the first gaps to appear. Only took the unwavering repetition of orbital patterns to empty them further. And only took sustained gravitational whispering from Jupiter to maintain their shape across epochs. The quiet irony persists that these apparent voids reveal the belt's structure more clearly than the asteroids themselves. The narrative moves deeper into the mathematics of these spaces. In the 3-to-1 resonance, where an asteroid completes 3 orbits for every one of Jupiter's instability, amplifies quickly, making the region nearly empty. In the 5-to-2, the effects are gentler, producing a partial gap where bodies drift in and out over time. Each resonance applies a slightly different rhythm, as though playing variations on a single celestial theme. Their influence shapes not only orbital eccentricity, but inclination, gradually pulling some bodies upward or downward away from the midplane, until their paths intersect the gravitational influences of Mars or Jupiter, and they are moved outward once again. These motions occur so slowly that even geological time seems impatient by comparison. The belt remains calm, unchanging in appearance, while underneath this stillness, the orbits of countless small bodies drift imperceptibly. The narration lingers on the reality that these migrations often send asteroids toward chaotic zones where gravitational influences overlap, creating pathways that may eventually lead them out of the belt entirely. Some wander into the inner solar system as near-Earth objects, though their journey spans millions of years and involves countless gentle adjustments, never a single decisive moment. The belt expresses this quiet movement like the tide and ebb and flow, shaped by forces too vast to be felt but too persistent to ignore. A gentle modern analogy appears like a soft reflection. The Kirkwood gaps resemble seats in a vast auditorium, where the harmonic vibrations of the structure make sitting unbearable, causing occupants to drift toward more comfortable places, not out of urgency but by subtle nudges that accumulate over time. The belt's broader structure emerges through this contemplation. Asteroids cluster in semi-major axis ranges, where resonances are absent or weak, forming broad bands of relative stability. Between these bands lie the gaps, silent corridors where orbits refuse to settle. Temperature composition and size distribution often differ slightly between these regions. not because the gaps themselves hold any physical quality, but because the processes that remove material also shape the neighbouring populations. Shadows drift across asteroid surfaces again as their rotations continue without care for the larger patterns within which they move. Each stone follows its path without awareness of the mathematics shaping the emptiness around it. Even the smallest fragments obey the same laws, drifting into or out of resonant regions depending on tiny forces such as the Yarkovsky effect, which slowly alters orbits through uneven thermal radiation. Over millions of years, this faint push can deliver a pebble-sized fragment into a resonance and eventually guide it far from the belt. Another soft irony surfaces: the emptiness of the gaps depends on the presence of countless interactions. Another emerges that the belt structure is defined not by what remains, but by what has already left. And a third follows gently that absence becomes the clearest sign of gravity's influence. Time stretches again. The belt's resonant patterns remain stable even as individual objects drift through them, like sand grains sliding down the slope of a dune, while the dune itself keeps its shape. Observing these patterns is not unlike reading the faint outlines of geological layers in a cliffside, each gap a relic of processes that continue without pause, shaping a structure that appears static only because change happens too slowly to witness directly. The narration glides into a deeper contemplation of the three-dimensional nature of these gaps. While they are often represented as simple radial voids, they actually span ranges of inclination and eccentricity, creating complex surfaces through orbital space. These surfaces define where long-term stability can exist and where it cannot, acting as invisible boundaries that fragment families cross as they disperse. When fragments cross these boundaries, some remain stable while others wander outward or inward, their paths shaped by the oscillations that resonances induce. These motions resemble slow breath cycles, expanding and contracting, orbital parameters through gravitational rhythm. A quiet mystery lingers regarding the exact rate at which asteroids drift into resonances and how frequently they escape. Collisions, thermal forces, and interactions with dust and plasma all play roles, yet the precise proportions of these contributions remain open to refinement. The gaps stand as silent records of these uncertainties' patterns, carved by processes understood in principle, but not fully mapped in detail. The contemplative tone holds steady as the narration returns to the central imagery of the belt. Stones drift on both sides of the gaps, following paths written long before any living being observed them. Their motion continues without intention, guided by the steady hand of gravity, by thermal guidance, by gentle perturbations, by time. The gaps remain shaped by what leaves defined, by what cannot stay always present, even though they contain almost nothing at all. The section settles now, drifting into a soft recognition that the Kirkwood gaps are not mere absences, but part of the belt's identity, subtle spaces where gravity has written silence into the structure of stone. The narration drifts onward into regions where the stones themselves begin to reveal the long memory of collisions, each fragment carrying subtle marks of events that no longer exist except in these quiet records. Worldlets with shattered histories move through sunlight with unhurried grace, their surfaces broken, ridged, and cratered in ways that speak to origins shaped more by impact than by growth. In the asteroid belt, fragmentation is not an event but a condition, an identity formed through billions of years of gentle disruption. Every asteroid here, from the smallest shard to the largest surviving protoplanet, holds echoes of ancient worlds that never fully formed, worlds whose potential was slowly undone by repeated collisions, guided by gravitational choreography. A simple fact settles softly into place: most asteroids are fragments of once larger parent bodies that broke apart during high-velocity impacts in the early solar system. These breakups occurred when material was still abundant and orbital paths were more chaotic, allowing collisions to occur with enough energy to reshape or completely shatter nascent objects. The debris scattered through orbital space, later reaccumulating into clusters, or remaining solitary depending on mass velocity and the gravitational influence of nearby bodies. Light glides across a fractured asteroid, now exposing layers that once lay deep within its parent body. Some regions appear smooth, the result of regolith slowly settling over crater rims. Others show jagged edges, where fresh material was exposed by more recent impacts. A lesser-known detail emerges. Many asteroids reveal spectral signatures indicating that their interiors once reached temperatures high enough for partial melting, a process driven by short-lived radioactive isotopes like aluminum-26. This internal heating created differentiated structures, cores, mantles, and crusts, suggesting that some asteroids were once miniature worlds geologically alive for brief spans of cosmic time. The fragments now drifting here are reminders of that early activity, bearing textures shaped by processes long extinguished. Yet a quiet mystery lingers, subtle and unresolved. The exact sequence of collisions that produced today's asteroid families remains partly hidden. Researchers piece together these histories by studying composition, orbital clustering, and thermal changes. Yet the timeline is difficult to reconstruct because fragments disperse, experience further impacts, and wander into resonances. Some families remain tightly grouped. Others are now so spread through orbital space that only fragments of their story remain legible. The belt becomes an archive with missing pages, yet the surviving ones carry quiet depth. Only took a few tens of millions of years for the early collisions to erase the original architecture of the belt. Only took countless impacts to produce the rubble-like structure seen today, and only took billions of years of continued gentle fragmentation to maintain this shattered equilibrium. The narrative touches one of these broken bodies, imagining the slow turning of a surface carved by overlapping crater rims. Some craters appear so old that their boundaries have softened, reshaped by the micrometeorite bombardment. Others are sharp-edged, the result of more recent impacts that lifted small plumes of dust into the thin surrounding void. The dust settles back slowly, unhurried by the atmosphere, forming a fine regolith layer that blankets the surface with muted greys and carbon tones. Regolith on an asteroid behaves differently from that on airless worlds like the Moon. With weaker gravity, grains settle loosely, forming porous layers that may shift with even minor seismic vibrations caused by small impacts or thermal expansion. A gentle analogy drifts forward. The surface behaves like a pile of loosely gathered ash, easily disturbed, quietly resettling into new shapes with each soft disturbance. The narration deepens into observations of asteroid shapes. Many are irregular, stretching into elongated or bifurcated forms that hint at their past as fragments torn from larger bodies. Some appear to be contact binaries, two pieces that gently collided long ago and fused together under low gravity, producing bodies that resemble stones pressed together by time rather than force. These shapes speak of collisions that did not end in destruction, but in quiet merging, a reminder that even disruption can produce new unions when conditions slow the final stages of impact. A soft irony rises. The belt's most fractured objects hold the clearest clues to its history. Another follows that destruction created the diversity observed today. And a third emerges that the quiet drift of fragments now appears serene only because the violence that shaped them lies far in the past. The narration observes how asteroid families preserve these histories. When a parent body shatters, its fragments initially share similar orbital elements: semi-major axis eccentricity, inclination-forming clusters that remain identifiable for millions or even billion of years. Over time, thermal forces such as the Yarkovsky effect push smaller fragments outward or inward, gradually dispersing the family and stretching it across orbital space. Some families become elongated bands, others blend into the general asteroid population. The very existence of these families reveals that fragmentation is an ongoing process. Fresh families have been identified with ages less than 10 million years, showing that collisions continue even today, though far less frequently than during the solar system's youth. Shadows drift over an ancient body as the sun slowly rotates beneath it. The stone absorbs heat on its sunlit side and releases it as it turns into darkness, creating small thermal contractions that cause fractures to widen. Over countless cycles, these stresses break off pebbles and dust, adding to the belt's cloud of fine material. A single day-night cycle on an asteroid may seem uneventful, but over billions of repetitions it shapes surface layers with a quiet persistence. The scene widens to include one of the largest asteroids, Vesta, whose enormous south polar basin reveals a colossal impact that nearly shattered the world. The debris from this event forms the Vesta family, scattered yet distinct many fragments orbiting far from their parent body. Spectral measurements connect them through shared mineralogy, showing that even separated by millions of kilometers, fragments bear clear genetic ties to their origin. A gentle mystery persists about how often such giant impacts occurred, and whether some families have been erased beyond recognition through subsequent collisions. The belt holds these uncertainties softly, offering clues but not complete answers. The fragmentation continues in subtle ways, space weathering darkened surfaces, gradually altering reflection spectra. Micrometeorites pepper the regolith with new microcraters. Occasionally, a larger impact reshapes a fragment's spin rate, making it tumble in complex rotations. Some bodies rotate so quickly that loose material migrates toward the equator, forming ridges or lobes reminiscent of slow landslides. These processes remind the listener that the belt is not static, even though its pace seems slow beyond measure. The belt's shattered bodies also reveal something about planetary evolution. Meteorites that fall to Earth originate from these asteroids, carrying samples that show the chemical diversity of early solar system materials. Some are carbon-rich with organic molecules, others are iron-nickel fragments of ancient cores. Still others are primitive stony meteorites that preserve unaltered nebular material. These samples act as gentle emissaries from the belt, providing insight into histories otherwise inaccessible. A soft irony returns, though the belt is distant and quiet. Pieces of it reach Earth more often than most celestial features do. Though it is largely unseen by human eyes, it becomes one of the most studied regions through these tiny messengers. And though its fragments drift in deep darkness, they illuminate planetary science more than many brighter bodies. As the narrative settles, it holds on to one final recognition. Each asteroid is both a survivor and a relic, shaped by the collisions that erased earlier identities, yet created new ones. Their shattered histories form a mosaic of early solar system events, preserved not through intention, but through the gentle persistence of fragments that continue orbiting long after their parent bodies vanished. The belt remains a region defined not by what it built, but by what it broke. Yet in that breaking, it offers a quiet, contemplative record of ancient processes that still echo softly through space. The narration drifts now into the slow machinery of collisions that has shaped the asteroid belt across its entire lifetime, a process so patient and persistent that it becomes less an event than an atmosphere, a quiet presence that moves through every orbit. Here impacts occur not as sudden catastrophes, but as rare rhythmic notes played across millions of years, gently transforming bodies into fragments and fragments into dust. The belt behaves like a vast ancient mill, where stone grinds stone in near silence, producing the fine particulate haze that fills the region and the broken surfaces that characterize nearly every world let drifting through this space. A simple grounded fact takes form with steady calm. The asteroid belt loses mass over time due to collisional grinding, with large bodies slowly eroded by smaller ones, and smaller ones reduced further into dust that is eventually swept away by solar radiation pressures. This slow collision machine operates without pause yet without urgency, guided by orbital overlaps, slight inclinations and velocities that, while immense, translate into infrequent but consequential encounters. Light glances off rotating fragments, revealing where ancient strikes have left scars, ridges, and crater chains. The silence of this place is not an absence of activity, but a reminder that change here occurs on intervals too long for immediate perception. A lesser-known detail glides quietly into view. Many small asteroids are not solid objects, but rubble piles, loose aggregations of boulders and dust held together only by their own delicate gravity. When struck, they do not behave like monolithic stones. Instead, they absorb and redistribute energy in complex ways, sometimes shedding material, sometimes reconfiguring their shape, sometimes spinning faster or slower depending on how the impact altered momentum. These rubble piles represent an advanced stage of fragmentation where repeated collisions have dismantled former structures until only reassembled remnants remain. Their internal voids and low densities reveal the hidden softness of these objects, contradicting the perception of the belt as a realm of hard stone. Yet a gentle scientific mystery lingers how exactly rubble piles respond to impacts across different scales. Laboratory experiments and simulations offer glimpses, but the low-gravity environment cannot be replicated perfectly, leaving precise details of how these bodies fragment, reaccumulate, or drift after collisions partially unresolved. Some appear surprisingly resilient, others disperse with minimal provocation. The belt keeps these uncertainties intact as though reminding observers that even the smallest structures hold complexities not easily captured by models. Only took the earliest 100 million years of the solar system for collisions to dominate the belt's evolution. Only took Jupiter's gravitational stirring to increase velocities enough to encourage fragmentation over accretion. And only took billions more years for the belt to settle into its current state of slow grinding equilibrium. The narrative follows the path of a fragment wandering through orbital space. Its motion aligns with the ambient patterns of the belt, intersecting with other objects in rare encounters. Most pass by without interaction, separated by distances so large that even chance seems too strong a word. But occasionally paths intersect closely enough for the faint pull of mutual gravity to alter trajectories, and more rarely still a collision occurs. In the thin light of the sun, two fragments meet at speeds of several kilometers per second, enough energy to shatter even large bodies. The impact produces new shards that drift outward in a cloud, each traveling into its own orbit. Their velocities slightly altered by the collision. Some reaccumulate into clusters, others drift far enough from their siblings that they become solitary wanderers. The motion remains tranquil in appearance because space has no medium to transmit the chaos of the impact. There is no sound, no shock wave, only the silent dispersal of matter. A soft modern analogy surfaces, gentle and unobtrusive. The belt behaves like an immense slow-moving construction site, where structures are continuously built, dismantled and rebuilt, not through intention but through the quiet persistence of mechanical processes. Over time, collisional families emerge, spreading gradually like the branches of a tree whose leaves drift across a landscape shaped by wind and time. The narration lingers now on the distribution of collision sizes. Large impacts are extraordinarily rare, influencing the region only a handful of times across billions of years, yet their consequences echo across entire orbital populations. Medium-scale collisions occur more often, shaping the size distribution of asteroids and producing many of the families observed today. Smaller impacts, micrometeorite strikes, dust collisions, thermal stress fractures happen continuously, reshaping surfaces and contributing to regolith production without altering bulk structure. Each scale plays a role in the quiet shaping of the belt. A soft irony appears. The smallest impacts happen the most often, but their effects are the hardest to observe. Another irony follows that the largest collisions define the population but leave the fewest witnesses, and a third rests gently in the realization that the belt's calm present is maintained by the remnants of its violent past. The scene shifts to explore how thermal forces contribute to this slow machinery. The Yorp effect, a force created by the uneven emission of thermal radiation, can gradually increase an asteroid's spin rate. Over millions of years, this can cause rubble pile asteroids to shed material or even fission into two separate bodies. This quiet spin-induced fragmentation creates new clusters of objects without requiring a collisional trigger. It is a soft kind of disruption guided by sunlight rather than impact, reminding the listener that even light can act as an agent of change when given enough time. Light continues to brush across the belt, illuminating the delicate balance between structure and dissolution. The belt's largest worlds survive primarily because their gravity is strong enough to resist total fragmentation, yet even they bear the scars of major impacts. Smaller bodies lacking such gravitational strength remain vulnerable to the cumulative effects of many minor collisions. Over billions of orbits, these processes produce a size distribution that steadily shifts from larger bodies to smaller ones. Dust fills the spaces between stones created by impacts so small they become nearly invisible in records, but meaningful in their contributions to the belt's overall evolution. A gentle mystery rests in how often catastrophic collisions occurred during the solar system's early phases, and how many families have since dispersed beyond recognition. Some scientists propose that the belt once held far more mass, perhaps enough to form a planet, if not for Jupiter's disruptive influence. If so, the present belt is only a fragile remainder of a once bountiful region, a quiet afterimage of a failed world. The belt reveals clues, but never the full picture. The narrative passes now through areas where small fragments cluster temporarily, bound loosely by shared motion, before dispersing again as thermal forces and gravitational perturbations continue shaping their paths. These transient groupings resemble gatherings of drifting leaves on a calm pond, brought together by slow eddies, only to separate once those currents change. The belt's evolution continues through these ever-shifting arrangements, subtle in their immediacy, yet profound across time. Another soft irony emerges, that the belt's apparent stillness relies on constant motion, that its long-term structure depends on short-term disruptions, and that fragmentation, though often thought of as destructive, serves as the primary creative force shaping the region's identity. The section settles into a final, quiet awareness. The asteroid belt is not a relic frozen in time, but a dynamic environment where collisions, thermal drifts, and gravitational nudges interact continuously. Every stone carries a story written by impacts both large and small, Yet these stories contain no drama, no urgency, only the steady unfolding of processes that have shaped the region for billions of years. The belt remains a slow collision machine grinding gently onward in silence, maintaining itself through the same forces that slowly dissolve it. The narration drifts now into the quiet domain of metallic asteroids. Those fragments that carry iron hearts adrift in cold orbits, remnants of ancient bodies that once experienced internal heat strong enough to melt and separate heavy elements from lighter ones. In the faint sunlight, these metallic worlds shimmer with muted reflections, not bright like polished metal, but soft and weathered, their surfaces darkened by billions of years of exposure to cosmic radiation and micrometeorite impacts. They move without hurry, following orbits shaped by the steady pull of the Sun and the distant influence of Jupiter, revealing in their silence a deep and intricate history. A steady, scientifically accepted fact comes forward gently. Many M-type asteroids are thought to be exposed cores of differentiated parent bodies, worlds large enough in the early solar system to undergo internal melting, driven by short-lived radioisotopes such as aluminum-26. As these bodies melted, iron and nickel migrated toward their centers, forming dense metallic cores, while lighter silicates floated outward to form crusts and mantles. Collisions later shattered these worlds, dispersing fragments from each layer. Some mantle material became ordinary stony asteroids. Some crust material became porous carbon-rich objects. And some core fragments, rare and dense, became the metallic asteroids that drift through the belt today. Light slides over one such body, revealing surface textures shaped not by tectonic processes, but by an endless series of small impacts. The regolith that coats many silicate-rich asteroids is thinner or absent here, as metallic surfaces often release less debris when struck. Pits and shallow craters appear smoother, their shapes softened by repeated micrometeorite erosion. A lesser-known detail emerges quietly. Certain metallic asteroids exhibit strong radar reflections due to their high metal content, allowing scientists to map their shapes and surface roughness with unusual clarity. Radar signals bounce off their surfaces with a distinctive brightness, revealing blocky contours and sometimes highly irregular forms that would otherwise remain hidden in optical darkness. Some metallic asteroids may even contain small amounts of platinum group metals, though their distribution remains uncertain and sparsely sampled. A gentle, persistent mystery arises here, subtle and unresolved. Whether all M-type asteroids truly represent exposed cores, or whether some are unusual mixtures of silica to metal created through incomplete differentiation or impact-related melting. Spectral observations yield conflicting results. Some display clear features of metal-rich surfaces, others show hints of silicates or hydrated minerals unexpectedly present. This ambiguity reflects the complexity of early planetary processes, suggesting that the belt contains material shaped by multiple pathways rather than a single origin story. The uncertainties linger softly, allowing space for ongoing exploration and refinement. Only took a few million years after the formation of the solar system for differentiation to occur in these parent bodies. Only took a handful of catastrophic collisions to expose their metallic interiors. And only took the quiet passage of billions of years for these fragments to drift into orbits that now appear peaceful and unchanging. Their presence is a quiet irony. The densest, most resilient pieces of ancient worlds now move through the belt as some of the most isolated and unassuming objects. The narrative rests on the density of these asteroids, significantly higher than that of stony bodies. This density alters their rotational behavior, making some spin with surprising speed while others tumble chaotic. Metallic strength allows them to withstand forces that would tear rubble piles apart, maintaining cohesive structure even after impacts that scar their surfaces. The belt's metallic fragments thus persist where other objects might have crumbled. Though their persistence carries no intention, only the inevitability of physical properties playing out across deep time. A soft analogy arises. These asteroids resemble the exposed framework of ancient buildings long after walls and roofs have collapsed, leaving behind the quiet skeleton that remembers the structure even when the rest has vanished. Metal in this cosmic context becomes not a symbol of strength, but of vulnerability, an interior revealed because everything around it was lost. The narration drifts to asteroid Psyche, one of the most famous M-type bodies. Its surface shows brightness variations that hint at a mixture of metal and silicate, suggesting a world whose past was more complicated than a simple exposed core. Radar data reveals blocky cratered terrain, while spectral features remain enigmatic. Psyche embodies the uncertainties of these metallic worlds, part memory, part fragment, and part possibility. The gentle curiosity surrounding it reflects the broader mystery of how early planetary differentiation unfolded, how cores formed, and how collisions redistributed these materials. As sunlight sweeps across another metallic fragment, the thermal properties come into focus. Metal heats and cools, quickly creating steep temperature gradients between day and night sides. These gradients produce thermal expansion and contraction that can crack even resilient materials, slowly reshaping the asteroid's surface. Over billions of cycles, this subtle process enhances weathering, creating shallow fissures and releasing tiny metallic flakes that drift outward before settling back or escaping entirely. A gentle irony surfaces. The objects born from molten interiors are reshaped most strongly by temperature changes, so mild compared to their fiery origins. The motion of metallic asteroids through the belt also differs slightly due to the Yarkovsky effect, as their metallic surfaces emit infrared radiation differently than darker, more porous bodies. These subtle differences influence the trajectories of small metallic fragments, guiding them gradually toward resonances where Jupiter's gravitational influence may nudge them into new orbits. Some fragments may become near-Earth asteroids, though the journey spans millions of years and occurs without urgency. The belt continues to redistribute its metallic heritage through these faint thermal pathways. Another quiet observation glides into view. The distribution of metallic asteroids varies across the belt, with M-types appearing more often in the central region, though not exclusively. This distribution speaks to the scattering of parent bodies and the subsequent migration of fragments. It is neither random nor precisely patterned, a balance between early collisional events, gravitational stirring, and thermal drift. Shadows deepen across surface craters as the sun slowly rotates behind distant arcs of orbital motion. Metallic asteroids reflect this light with subdued sheen, their surfaces neither bright nor dark, but something in between, a muted glow that fits the contemplative rhythm of the belt. No drama accompanies their drift, no tension marks their history. They simply move, bearing the innermost material of worlds that tried briefly to become more than fragments. A gentle mystery lingers at the threshold of understanding how many differentiated bodies once existed in the early solar system, and how many were entirely destroyed. Meteorites that fall to Earth include iron-nickel samples that likely originate from these asteroids, yet the number of unique parent bodies inferred from these meteorites suggests that dozens, perhaps hundreds of differentiated worlds once orbited the Sun. Their cores now lie as scattered metallic relics, while their mantles and crusts distribute across stony populations. only took a fraction of cosmic time for these worlds to rise and fall, leaving behind these dense and silent remnants. The section slows, now settling into a final contemplative moment. Metallic asteroids drift through the belt like quiet, enduring notes in a symphony of stone, their iron hearts carrying the memory of molten interiors, violent shattering and long calm. They persist not as threats or omens, but as unassuming witnesses to the earliest ages of the solar system. They neither seek nor resist change. They simply hold their structure as time flows gently around them. The narration drifts now toward the darker carbon-rich regions of the asteroid belt, where the faint breath of water lingers within ancient stones that once carried the earliest whispers of hydration through the young solar system. These C-type asteroids, muted in colour and low in reflectivity, absorb most of the light that falls upon them, giving them an appearance softer and deeper than their stony or metallic counterparts. They move through their orbits with quiet steadiness, shaped by the same slow gravitational rhythms as the rest of the belt, yet carrying within them traces of minerals that formed in the presence of water long before Earth's oceans existed. A simple scientifically accepted fact settles softly into place. Many carbonaceous chondrites meteorites derived from C-type asteroids contain hydrated minerals formed through aqueous alteration, meaning that water once interacted with the parent body's rocky material, altering their chemical structure. These minerals preserve the faint memory of water, not as liquid coursing through vast channels, but as microscopic interactions within porous rock activated by heat from early radioactive decay. In this context, water was not a flowing presence, but a chemical partner shaping minerals quietly within sealed interiors of small bodies. Light that falls upon these asteroids is absorbed rapidly by their dark carbon-rich surfaces, revealing little in visible wavelengths, but offering clues through infrared spectra. A lesser-known detail emerges. Many C-type asteroids carry organic compounds complex enough to include amino acids, though not in biological arrangements. These molecules formed naturally through chemical pathways in early solar system environments preserved within these stones for billions of years. Their presence offers a glimpse of the chemical richness that existed before life emerged anywhere, a reminder that organic chemistry is a natural process woven into planetary formation, not an anomaly. Yet a quiet scientific mystery lingers at the heart of these bodies: how much water they once contained, and in what form. Some appear to have held significant amounts of ice that melted through internal heating. Others show only slight alterations, suggesting brief or incomplete hydration. The exact balance remains uncertain because the record preserved in meteorites reflects both original composition and the long journey from asteroid to Earth. Some fragments experienced heating during atmospheric entry, others were altered by terrestrial exposure. The belt's C-type asteroids thus hold stories partially readable, partially obscured, inviting continued exploration. Only took the first few million years of solar system history for these bodies to acquire their hydrated minerals. Only took gentle internal heating to initiate water-rock interactions, and only took billions of years of drifting silence for the faint breath of water to remain locked within them as an echo of early conditions. In the vast stillness of the belt, these asteroids become quiet reservoirs of ancient chemical environments that no longer exist elsewhere. The narration settles on the surfaces of a typical C-type asteroid, observing the muted interplay of shadows. The regolith is dark and porous, composed of fine grains that crumble easily under minimal stress. This fragile structure reflects the volatile, rich nature of the material shaped by the low-temperature processes of the early solar system, rather than the high-temperature melting that produced metallic or stony asteroids. The grains cling loosely to one another, forming a surface layer. that shifts with impacts or thermal cycling. The porous texture allows heat to penetrate slowly and unevenly, creating patterns of thermal stress that gently break particles apart over time. A soft analogy arises. These surfaces resemble the charred remnants of driftwood, washed ashore, darkened and fragile, shaped by long exposure rather than abrupt events. Yet the comparison remains symbolic. These stones have never known oceans or air, only the cold vacuum in which they slowly weather. The narrative moves deeper, tracing how C-type asteroids contribute to the distribution of water in the inner solar system. Collisions send fragments inward, some eventually intersecting Earth's orbit. Meteorites derived from these bodies reveal isotopic signatures of hydrogen that closely match those in Earth's oceans, suggesting that early bombardment by carbonaceous asteroids may have contributed to the planet's initial water inventory. This idea remains grounded in peer-reviewed research, though the exact proportion of water delivered in this way remains a topic of quiet debate. It is a soft irony that Earth's oceans, perhaps the most defining feature of its surface, may trace part of their origin to these dark, unassuming stones drifting in silence between Mars and Jupiter. Another soft irony follows. The bodies thought least likely to hold water are among those that preserve its oldest chemical traces, and yet another rests gently in the awareness that these cold, dry worlds may have provided the volatile elements necessary for life to flourish elsewhere. Sunlight continues its thin sweep across these asteroids, revealing subtle variations in albedo, caused by patches of different mineralogy. Some regions are darker, perhaps richer in carbon, or altered by past interactions with water. Others reflect slightly more light, hinting at exposed silicate patches. These variations remain faint, requiring careful observation through telescopes and spacecraft to parse. The silence of the belt magnifies their subtlety, allowing each detail to be contemplated without distraction. A gentle mystery remains regarding how often water existed in liquid form within small early bodies. While heat from radioactive decay could melt internal ice, the duration of these warm phases remains uncertain. Some models suggest only tens of thousands of years. Others allow longer periods where pockets of liquid water might have existed. These durations are small compared to cosmic timescales, yet sufficient to alter mineral structures forever. The belt carries these brief windows of liquid history like memories etched into stone. The narration moves next into the structures of hydrated minerals themselves, phyllosilicates, carbonates and sulfates each, a record of water-rock interaction. Their presence indicates environments where temperature, pressure, and chemical composition aligned just long enough to form stable hydrated phases. These minerals crumble easily now, fragile after billions of years of space exposure. A soft irony emerges. Minerals formed through water become brittle under the unending dryness of space, preserving their origins, even as their surfaces weaken. The contemplation expands across the belt, observing clusters of C-type asteroids that may share origins from common parent bodies. These families drift together in orbital parameter space, though their members are separated by millions of kilometers. Their shared spectral features reveal a common history of hydration and carbon-rich chemistry, suggesting parent bodies once held both water and heat, sufficient to alter their interiors. Over time, thermal drift and resonances gradually disperse these fragments, mixing them with unrelated populations. Yet compositional fingerprints remain, allowing scientists to trace their lineage long after dispersal. Shadows stretch slowly across these bodies as the sun continues its steady arc relative to their rotations. The day-night cycle brings temperature changes sharp in numerical contrast from over 100 degrees Celsius in sunlight to far below freezing in shadow, but gentle in effect due to low thermal inertia. These extreme variations contribute to surface breakdown, yet the interior remains cold and stable, holding hydrated minerals intact. A gentle observation drifts forward even in a region defined by dryness and cold. The memory of water persists in forms so illicit they require close study to detect. Another soft observation follows that these asteroids, though chemically rich, remain visually unremarkable, offering their secrets only to those who look beyond surface brightness. A third observation lingers: the faint breath of water, once active deep inside these bodies, no longer flows, but remains locked within minerals that drift silently through the belt. The narrative slows, now settling into the calm presence of these dark, quiet worlds. Their contribution to the solar system is not expressed through brilliance or mass, but through memory, chemical, isotopic, and structural. They hold the whisper of early water, the fingerprint of organic chemistry, and the trace of processes that shaped planetary development. Their orbits can, without urgency, carrying them around the sun as they have done for billions of years, their faint breath of water lingering as a reminder that even the driest regions of space contain echoes of the conditions from which life may one day emerge. The narration drifts now into the quiet architecture of lineage within the asteroid belt, settling gently among the hidden darkness of the family's clusters of bodies that share common origins, yet wander through space separated by millions of kilometers. These families do not announce themselves through visible proximity. Instead, they reveal their unity through orbital patterns and spectral signatures, subtle echoes of a shared past. Each family begins with a single event long vanished from memory, the breakup of a parent body whose internal composition and history are now preserved only in the fragments that drift through the belt like dispersed chapters of an ancient book. A simple, scientifically accepted fact unfolds softly. Asteroid families are identified through clusters in orbital elements, semi-major axis eccentricity, and inclination combined with similarities in composition. These groupings form the fingerprints of past collisions. Even as individual fragments separate over millions of years, their shared parameters remain anchored to the orbital center of the original parent body, offering a quiet map of their origin. The existence of these groupings confirms the belt's long history of catastrophic disruptions and gradual dispersal, shaping a structure far richer than a random scattering of stones. Sunlight glides across one such family, illuminating surfaces that vary in brightness but share similar spectral features. Some fragments reflect light with muted carbon tones, while others appear stony or metallic depending on the parent body's nature. These similarities become the clues that tie them together, allowing scientists to reconstruct family trees of the belt. A lesser-known detail emerges, like a faint glimmer. Some families, such as the Corinne family within the larger Coronis group, are remarkably young, only a few million years old, offering fresh insight into how fragments disperse after breakups. Because they are young, their orbital clustering remains tight, their dispersal pathways still early in development. Such families act as time capsules within the broader belt, revealing processes otherwise smeared across billions of years. Yet a quiet mystery lingers: how many families have vanished completely, their fragments dispersed by thermal drifts, resonant interactions, and subsequent collisions until no recognizable clustering remains. Most asteroids today may come from families long dissolved beyond identification, their common origin erased not through disappearance but through the slow blending of orbital parameters. Computational models suggest that early collisions were far more common and more energetic than those occurring now, implying that many ancient families lie hidden within the diffuse population their signatures lost. The belt thus holds countless untraceable histories preserved in fragments, but not in form. Only took a single collision to create each family. Only took billions of years for thermal forces like the Yarkovsky effect to stretch them across orbital space. And only took billions of years for many families to fade into obscurity. The narrative rests gently on the Yarkovsky effect, now observing how the uneven emission of infrared radiation slowly shifts asteroid orbits. Small fragments, especially those less than a few kilometers in diameter, drift inward or outward depending on their rotation direction. Over time, this drift elongates families, scattering their members along semi-major axis lines, while retaining original inclination and eccentricity signatures. It is a slow, almost imperceptible movement, yet it shapes the belt as profoundly as collisions. Sunlight, faint and steady, becomes an agent of migration across epochs. A soft analogy emerges. Asteroid families behave like petals released from a flower carried by a slow and persistent wind. While they may travel far from one another, the shape of their dispersal reflects the structure from which they originated. Orbital clustering remains the gentle imprint of that structure, even as fragments drift into new rhythms. The narration glides toward the darker puzzle of hidden families. Some have been identified only through spectral analysis, where similar mineral signatures reveal common heritage even when orbits appear scattered. Others are inferred from meteorite types found on Earth that suggest many more parent bodies existed than currently recognized in asteroid populations. Iron meteorites, for instance, point to dozens of differentiated parent worlds whose fragments do not form identifiable clusters today. Their families evaporated long ago into the diffuse belt, leaving behind only scattered survivors with no visible trace of their kinship. Soft ironies surface. The belt's most ancient families are often the least visible. The most fragile bodies preserve the clearest signatures of their past, and the quietest populations may hold the deepest histories. The narration now observes the slow evolution of a well-known family, the Flora group in the inner belt. Its members share stony compositions and similar orbital characteristics, suggesting a large parent body that broke apart long ago. Fragments drifted into resonances, some eventually becoming near-Earth asteroids. Meteorites derived from such families carry crystalline structures that reveal thermal histories, cooling rates, and exposures to cosmic radiation. In this way, asteroid families extend their influence beyond the belt, delivering small messages to Earth in the form of meteoritic samples. A gentle mystery remains regarding how many families contribute to the present near-Earth population. Some models suggest that certain resonances preferentially receive fragment input from specific families, making them the silent sources of many Earth-crossing asteroids. Yet the connections are difficult to trace across long timescales because orbital chaos obscures past pathways. Still, the belt continues offering these fragments with quiet regularity, driven not by intention but by the slow mechanics of drift and resonance. Light drifts across the surfaces of family members that have remained within the belt. Their shapes range from nearly spherical to steeply angular, depending on their internal strength and collision history. Some remain intact rubble piles. Others show exposed layers where past impacts peeled back surfaces like thin sheets of stone. As time stretches, each fragment evolves individually while continuing the collective story of its family, both bound and unbound by gravity. A soft observation forms families reflect both unity and dispersal stability and change memory and forgetting. They move as individuals yet remain connected by patterns only visible through careful study. Another observation arrives that fragmentation, seemingly destructive, becomes the mechanism through which these histories survive. And a third follows quietly that the belt holds its genealogies not through clustering alone, but through the enduring consistency of physics that governs their drift. The narrative shifts gently to the role of collisions within families. Large fragments may collide with smaller ones, reshaping both and occasionally creating subfamilies. Over long intervals, such interactions produce complex branching structures similar to genealogical trees, but expressed in orbital rather than biological terms. These branching families confirm the belt's dynamic nature, a region where identity evolves yet retains echoes of original structure. As the section nears stillness, it widens to encompass the belt's hidden genealogies as a whole. Families exist not as clusters of stones flying together, but as quiet relationships between fragments whispering of a common origin. Shadows drift slowly across them as they continue their orbits, each one carrying its own small record of the parent body that once existed. The hidden darkness of the families lies not in obscurity, but in the subtlety of their presence. A structure woven from absence dispersal and ancient ties carried silently through time. They drift on bound by memory, yet free in motion, waiting in their quiet way for the patterns of their origins to be recognized or to fade gently into untraceable dispersion. The narration moves now into the slow, pervasive influence of the Yarkovsky effect, a force so faint that it can only be understood through deep time, yet so steady and persistent that it quietly reshapes the asteroid belt's architecture. Here, sunlight becomes not just illumination, but motion guiding small bodies through space, with a touch so soft it seems almost imagined. The effect arises from the simple physics of heat as an asteroid absorbs sunlight and re-emits that energy as infrared radiation. The uneven release of photons exerts a tiny thrust. If the asteroid rotates, this thrust becomes directional, gently nudging its orbit inward or outward. Nothing dramatic happens in any single moment. No asteroid leaps from its path or accelerates perceptibly. Instead, each tiny push accumulates across millions of years, producing migrations so gradual they resemble changes in the drift of dust or the slow settling of silt in deep oceans. A grounded fact settles quietly for small asteroids less than a few kilometers in diameter. The Yarkovsky effect can dominate long-term orbital evolution, shifting semi-major axes by tens of kilometers per million years. Over cosmic timescales, such drifts can deliver bodies into resonances, where gravitational influences from Jupiter or Saturn then take over, pulling fragments into new orbital regimes. The combination of thermal drift and gravitational resonance becomes one of the most significant pathways through which the belt supplies near-Earth objects. Even so, this process remains peaceful and indifferent, requiring no sudden events, only sunlight, time and rotation. Light sweeps across a small asteroid, now warming one side while the other cools. As the body rotates, each region absorbs heat before releasing it into space, creating an asymmetric emission pattern. The direction of drift depends on the sense of rotation. Prograde rotators tend to drift outward, while retrograde rotators move inward. A lesser-known detail drifts forward. The magnitude of the Yarkovsky effect depends not only on rotation, but also on thermal inertia, how quickly a body heats and cools. Regolith-covered asteroids with fluffy insulating surfaces experience different patterns of heating compared to dense, bare rock. Thus, two fragments of similar size may drift at different rates, their paths diverging quietly over time. An additional nuance lies in shape. Irregular forms concentrate heat at certain facets, modifying drift in ways that numerical models continue to refine. a gentle scientific mystery remains the exact contribution of the Yarkovsky effect to the long-term distribution of asteroid families. While models show general patterns, uncertainties in surface composition, spin states, and thermal properties make the precise reconstruction of drift histories elusive. Scientists can trace broad tendencies but rarely exact trajectories. The belt, with its mixture of dark, carbon-rich bodies and bright, stony surfaces, exhibits a diversity of Yarkovsky responses too nuanced for simple classification. Only took a few thousand years for the first measurable shifts to begin after fragments formed. Only took a few million years for these shifts to alter orbital clusters, and only took billions of years for entire families to elongate across semi-major axis space like ancient ink strokes brushed lightly across celestial parchment. The narration deepens into this drift, observing a small stony fragment less than a kilometre across. Its rotation rate changes slowly due to the Yorp effect, a torque arising from the uneven reflection and emission of radiation. Over time, Yorp can spin a body faster or slower, modifying the Yarkovsky drift direction or magnitude. In extreme cases, Yorp can spin rubble pile asteroids so rapidly that they shed material, creating binaries or clusters of small fragments. Light glints across this fragment as it turns its surface, warming unevenly, each thermal cycle contributing to the minute, persistent push that alters its orbit. The belt offers no resistance. Everything here moves in response to forces too delicate for immediate observation. A soft analogy arises. The Yarkovsky effect is like the slow sway of a drifting leaf, guided more by the warmth of sunlight than by wind. Its path shifting not from an external push, but from the leaf's own exchange of energy with its surroundings. The narration expands to the collective consequences of thermal drift. Over time, asteroid families stretch into elongated shapes in orbital diagrams with smaller fragments drifting further than larger ones. This size-dependent dispersion becomes one of the key signatures used to estimate family ages. Young families appear tightly clustered, while older ones stretch across a wide range of semi-major axes, shaped by billions of cycles of heating and cooling. Yet even within these elongated structures, some fragments buck expectations due to variations in surface texture or spin, adding complexity to the family's overall shape. A soft irony emerges. Sunlight, which seems too gentle to move stone, becomes one of the primary agents of long-term migration. Another irony follows, that the smallest bodies feel the strongest influence from this subtle force. And a third rests quietly in the realization that the same star that forged the early solar system continues shaping its smallest remnants not through eruptions or storms, but through warmth. The narration follows one such drifting body as it approaches a resonance. Here, gravitational interactions amplify the Yarkovsky-induced shift. At the boundary of a resonance, even a slight push can increase orbital eccentricity, slowly modifying the orbit until the asteroid becomes unstable. Over time, it may be pulled inward toward Mars' crossing orbits or outward to Jupiter's domain. Some find their way into the chaotic regions that link the main belt to the near-Earth object population. The entire journey may span tens of millions of years, yet at no moment does the asteroid experience anything more dramatic than a quiet change in its orbital parameters. The belt continues to offer these bodies into resonant channels, not through active processes, but through the combined whisper of light and gravity. The narrative settles briefly on the role of thermal drift in shaping the presence of meteorites on Earth. Many meteorites that reached the planet, both stony and metallic, began their journey through Yarkovsky-induced migration. Their parent fragments drifted into resonances before entering orbits that intersected Earth's path. Thus, the presence of meteorites in human hands reflects not only the mechanics of atmospheric entry or the geology of parent bodies, but also the slow, gentle influence of sunlight across unimaginable timescales. Another quiet mystery lingers. The precise spin states of most small asteroids remain unknown, making predictions of their long-term drift uncertain. Some bodies tumble chaotically, reducing or altering thermal effects. Others maintain stable rotations that enhance predictable drift. Missions such as OSIRIS-REx and Hayabusa 2 have begun measuring these properties, yet the vast majority of the belt remains unobserved, leaving its thermal evolution partly hidden. Shadows slip across drifting fragments, marking the slow rotation of bodies, shaped not by internal engines but by the interplay of sunlight's surface texture and the emptiness of space. Thermal conduction runs shallow, never penetrating deeply into these stones, allowing their interiors to remain cold even as surface temperatures cycle rapidly between sunlight and shadow. These thermal gradients, subtle as they are, write the future paths of countless fragments and define the quiet dynamic of the belt. The narration widens to acknowledge the cumulative beauty of this process. The Yarkovsky effect is not dramatic, visible, or loud. It does not reshape landscapes or trigger collisions directly. Instead, it offers a gentle continuity, a slow redistribution of matter that ensures the belt remains in flux. Through its action, fragments that form together drift apart, some toward resonances, some into near-Earth space, some into the outer belt, and some into regions where they remain for billions of years. The belt becomes a place where thermal energy and gravitational structure combine to create quiet pathways through which stone travels across epochs. The section settles now into a final moment of soft recognition. The Yarkovsky effect reveals that even the smallest details, the warmth of sunlight, the spin of a stone, the thermal inertia of regolith, shape the evolution of worlds. It shows that change can arise from patience rather than power, from accumulation rather than event. In the asteroid belt, this gentle drift continues without pause, guiding fragments across the range between Mars and Jupiter, with all the softness of a shadow moving across a quiet landscape. The narration now moves with quiet patience into the long, diffuse pathways that lead some asteroids from the calm expanse between Mars and Jupiter toward the inner solar system, following trajectories shaped not by sudden events, but by the cumulative whisper of gravitational and thermal forces. Here, the concept of a path toward Earth is not a corridor or a flow, but a gradual unfolding of orbital evolution. A body drifts for millions of years through the belt, pushed imperceptibly by the Yarkovsky effect, until one day its semi-major axis intersects a resonance. Even then, nothing dramatic occurs. The asteroid simply begins to experience tiny, repeated gravitational tugs from Jupiter or Saturn, altering its orbit step by steady step. Each nudge is negligible, yet together they can raise orbital eccentricity, tilt inclination, or shift the orbit inward. Over immense stretches of time, a fragment that once drifted in quiet stability becomes a wanderer, drawn into zones where chaos begins to shape its possibilities. A scientifically accepted fact settles gently. Most near-Earth asteroids originate from the main belt, delivered through resonances such as the 3-to-1 Kirkwood gap, the N6, secular resonance, and the 2-to-1 mean motion resonance with Jupiter. These resonances act like gateways, though not in any sudden or severe way. They simply amplify small perturbations stretching orbits until they intersect the region where Mars or Earth might gently alter their trajectories further. The journey involves no single decisive moment, but thousands upon thousands of orbital cycles, each one carrying a slight modification that over time becomes significant. Light drifts across a small stony fragment that has begun this long migration. At first, its orbit differs little from that of its family members, but as thermal drift nudges it slowly inward, it approaches the N6 resonance near the inner edge of the belt. There, the gravitational influence of Saturn subtly alters the precession of the asteroid's orbital ellipse. Over time, this resonance dramatically increases the asteroid's orbital eccentricity, stretching its path into a more elongated shape. Yet even this process occurs in silence. The asteroid feels no pull beyond the usual gravitational guidance, no change beyond the mathematics of orbits. A lesser-known detail emerges quietly. Many asteroids remain in resonances for only a few million years before drifting out again, their orbits reshaped but not fully destabilized. It is only a subset whose parameters shift enough that they wander into the inner solar system. Those that do may become Mars crossers first, then Earth crossers, though the transitions unfold slowly and without perceptible punctuation. The effect of each gravitational nudge resembles the faint sway of a pendulum disturbed gently and repeatedly over countless swings. A quiet scientific mystery lingers. The precise proportion of near-Earth asteroids supplied by each resonance remains uncertain, partly because many objects drifting inward encounter collisions, fragment further, or become lost in chaotic regions before reaching Earth-crossing orbits. Computer models simulate broad tendencies, but real trajectories depend on spin states, shape surface properties, and countless details impossible to track for every body. Thus, the path toward Earth remains a story of statistical flows rather than individually predicted journeys shaped by uncertainties that mirror the vastness of time itself. Only took a few billion years for these pathways to emerge, only took subtle gravitational harmonies to maintain them, and only took the faintest thermal pushes to feed them continuously with new fragments. The narrative deepens into the subtle interplay between Mars and the drifting fragments. Mars, though small, exerts resonant influences of its own. Some asteroids enter secular resonances, involving Mars's orbital precession, altering their inclination and eccentricity. Others cross the Martian orbit and experience repeated small perturbations that gradually change their path. These interactions do not resemble collisions of intention, but rather the passing of shadows across quiet ground, gentle, cumulative, and inevitable given enough time. A soft analogy forms the path toward Earth resembles a vast hillside where grains of sand occasionally slip downward, not because they were thrown or pushed, but because the gentle slope and subtle vibrations eventually encourage motion. In the belt, sunlight provides the slope gravity, the vibration and time the patience needed for the drift to occur. Shadows stretch across asteroid surfaces as they move deeper into regions where orbital chaos begins to expand. In these zones, small differences in initial conditions lead to divergent futures. An asteroid with a slightly different spin rate or thermal inertia might drift into a different resonance, leading it either toward inner or outer regions. This sensitivity underscores the delicate complexity of orbital evolution, a complexity that cannot be personified or dramatized, but only observed in its mathematical inevitability. A soft irony takes shape. The objects that pose potential risk to Earth begin their journey in one of the most stable regions of the solar system. Another irony that their arrival near Earth is not the result of sudden displacement, but the outcome of billions of years of gentle forces. And a third, that the very mechanisms that supply Earth with meteorites rich in scientific information are the same ones that occasionally deliver larger bodies into near-Earth space. The narration moves now to the long-term evolution of bodies once they become near-Earth objects. Their orbital lifetimes are short compared to the stability of the belt, often only a few million years, because interactions with planets rapidly modify their paths. Some collide with planets or the Sun, others are ejected into interplanetary space. Few remain in near-Earth orbits for long. This continual cycling means the near-Earth population is constantly renewed by the new arrivals from the belt, maintaining the dynamic exchange of matter across regions. The journey inward does not guarantee arrival near Earth. Many bodies drift outward, instead pushed into resonances that lead toward Jupiter's domain. Some become Jupiter family comets if they originate from icy outer regions. Others are scattered into distant orbits. But for those that enter the inner solar system, their presence becomes a quiet reminder of the belt's long connection to Earth. A connection formed not through intentional exchange, but through the shared gravitational architecture of the solar system. A gentle mystery lingers regarding the long-term behavior of small fragments that enter chaotic regions. While large-scale patterns are understood, the precise route of any individual grain or pebble remains unknowable due to the chaotic nature of those pathways. The belt contains countless such fragments, each with a unique spin-state shape and surface texture that gradually modifies its trajectory. Even the smallest irregularities, a slight wobble, a rough surface patch, can become significant over millions of years. Shadows glide softly over drifting fragments as their orbits lengthen and shift. Some bodies rotate irregularly, tumbling in patterns altered by collisions or thermal torque. This tumbling reduces the predictability of the Yarkovsky effect, adding to the uncertainty of their futures. Yet all these uncertainties remain part of the same quiet natural system, a system that requires no drama to produce profound change. The narration expands its scope to include Earth as merely one possible intersection along these drifting paths. The probability that any specific asteroid strikes Earth is extremely small, yet the probability that some asteroid will eventually do so remains non-zero when measured across geological time. This reality is neither threatening nor urgent. It is simply part of the solar system's long-term exchange of material. Earth itself bears the scars of past impacts, some enormous, some minute, each one a record of stones that completed their slow migration inward. These scars tell a story not of danger, but of participation in the broader evolution of planetary surfaces. The narrative slows further, taking a quiet breath as it acknowledges that Earth's own geology, atmosphere, and biological history have been shaped in part by these quiet arrivals. Meteorites contributed heavy elements, organics, and water. Larger impacts altered climates and ecosystems. These influences emerge not from dramatic forces, but from the patient unfolding of orbital mechanics. A soft observation rests here. The path toward Earth is neither a threat nor a promise, simply a natural outcome of the solar system's structure. Another observation follows that the journey of stone is shaped more by subtle forces than by violent ones. And a final observation lingers that Earth's connection to the belt is inseparable from the quiet mathematics of resonance and drift that define the region. The section settles into stillness, now acknowledging the long path that fragments take when they leave the quiet belt. Their journeys unfold at a pace that mirrors geological change, guided by forces that offer no urgency. These drifting bodies do not rush toward Earth. They merely follow the pathways written into space by sunlight and gravity, moving with calm, inevitable continuity. The narration moves softly now into the quiet awareness that within the wide, seemingly uneventful sweep of the asteroid belt, dormant threats exist not in the sense of imminent danger or hidden intention, but as natural possibilities embedded in the long rhythms of orbital evolution. These bodies drift in calm isolation, their paths stable across millions of years, yet their eventual destinies can shift subtly through the same quiet forces that shape every stone between Mars and Jupiter. The belt holds no malice, no agency. It merely contains fragments whose futures include rare pathways that lead inward toward the terrestrial planets. A gentle, scientifically grounded fact settles in potentially hazardous asteroids identified near Earth today are overwhelmingly fragments that once belonged to the main belt. Their presence in the inner solar system results not from violent ejection, but from the slow cumulative influence of thermal drift, secular resonances and gravitational encounters. The belt itself is peaceful. The trajectories that eventually carry fragments inward arise gradually through structural dynamics inherent in the solar system. Light drifts across dormant fragments deep in the belt, illuminating surfaces unchanged for eons. Many of these bodies have remained in the same orbits for billions of years, untouched by resonances. Their shapes are irregular, their surfaces darkened by space weathering, and their rotations shaped by ancient collisions. They drift with no sense of their potential to become Earth crossers tens or hundreds of millions of years in the future, their fates written instead in the slow mathematics of orbital change. A lesser-known detail emerges. Some of the most hazardous near-Earth objects share specific spectral signatures with distinct asteroid families such as Flora or Eulalia. These connections allow researchers to trace their origins, revealing that certain families lie near powerful resonances like N6. From such locations, fragments can drift quickly on geological timescales toward pathways that carry them inward. These family resonance linkages form quiet conveyor belts through which certain near-Earth asteroids are supplied. Yet a quiet mystery lingers regarding the exact efficiency of each family in producing potentially hazardous objects. Some models suggest that a handful of families dominate the supply. Others imply more distributed contributions. The uncertainties arise because thermal drift rates vary with size, shape and rotation, producing dispersion patterns that resist precise reconstruction. The belt holds these mysteries gently without urgency or fear, offering clues through fragment distributions and factual relationships that require long-term study. Only took the early solar system's turbulent beginning to create the initial conditions for these dormant threats. Only took billions of years of thermal and gravitational nudging to guide some bodies toward resonances, and only took the faintest adjustments in the orbital eccentricity for a fragment to become eventually a near-Earth traveller. Yet across all this time, the belt itself remains quite stable, largely unchanged in broad structure. The narration moves through regions where fragments turn slowly, their surfaces showing the patterns of long exposure. Some carry grooves or ridges from distant impacts. Others exhibit complex tumbling motions shaped by the Yorp effect. None anticipates future orbital drift. None displays any sign of movement beyond the steady arc set billions of years before. Even fragments that may one day wander inward show no indication of their role within the solar system's long-term rhythms. A soft analogy arises. These potential travelers resemble seeds caught in a gentle current. Most remain where they are suspended in calm water, but a few drift toward pathways where the current becomes stronger, carrying them gradually outward or inward. Nothing in the seeds themselves marks them as future travelers. It is only the patterns of the current that determine their movement. The narration deepens as the focus shifts to the complex structure of resonances that act as gateways. The N6 secular resonance near the inner edge of the belt is one of the most influential, capable of raising eccentricity until an orbit intersects Mars or Earth. Mean motion resonances such as the 3:1 or 5:2 serve similar roles, each pathway offering slightly different outcomes. Some deliver fragments into Mars-crossing trajectories quickly, others require long intervals before chaos takes hold. These resonances do not function as traps or engines, but as regions where gravitational harmonies amplify small motions, turning faint thermal drifts into meaningful orbital change. Within these resonances, bodies that were once dormant begin to experience subtle shifts. Orbital eccentricity increases gradually, inclinations oscillate, and perihelion distances drop closer to the inner planets. Yet this process remains slow unfolding across millions of cycles, always governed by the steady laws of celestial mechanics. The belt contributes new fragments to these resonant channels at a rate balanced by losses through impacts, ejections, and solar absorption. This equilibrium ensures that near-Earth populations are constantly replenished, not through sudden events, but through the quiet persistence of thermal and gravitational evolution. A soft irony emerges: the most stable region of the solar system becomes the source of its slowest moving hazards. Another irony that these objects pose risk only after spending the majority of their existence in deep calm. And a third that their journeys toward Earth pass unnoticed for the majority of their migration. The narration glides gently into the structure of the belt itself, noting how some regions are more likely to produce inward drifting fragments because of proximity to powerful resonances. The inner belt, especially the region near Flora and Vesta families, produces many near-Earth asteroids. Carbon-rich families in the outer belt contribute fragments to different resonances, capable of directing them inward as well. Even distant regions can supply travelers when their fragments drift into overlapping resonant webs. Light moves softly across these regions, revealing fragment populations shaped by both collisional events and long-term dispersal. Some bodies drift toward resonances only to be turned away by small perturbations that alter their drift direction. Others migrate steadily until capturing into a resonance that reshapes their orbits permanently. Each body's fate reflects a combination of its thermal properties, shape, rotation, and the dynamics of the region it enters. A quiet scientific mystery remains regarding the ultimate fate of many fragments that approach resonant boundaries. Some models suggest high probabilities of eventual planetary encounters. Others indicate long-term residence in chaotic pockets. The variability arises from the sensitivity of chaotic systems to initial conditions. This quiet unpredictability does not affect the broad statistical patterns, but renders individual futures unknowable. Shadows pass over one such fragment as it begins a slow transition toward a Mars-crossing orbit. Its path lengthens subtly, with each resonance cycle its perihelion dipping slightly closer to the inner planets. No event marks this shift, only the accumulation of tiny changes that slowly reshape the orbit. Once in Mars-crossing space, the fragment experiences occasional gravitational nudges from Mars, further modifying its trajectory. Over millions of years, some such bodies cross Earth's orbit. The narration rests on this understanding without embellishment. The potential hazard arises from natural orbital evolution, not intention. These bodies are neither hunters nor wanderers in any narrative sense. They are fragments following the mathematics of motion drifting, where the solar system's architecture guides them. A soft observation forms Earth's long-term risk from impacts is not exceptional but intrinsic to living within a dynamic planetary system. Another observation follows that dormant threats exist not as anomalies, but as expressions of natural orbital pathways. And a final one lingers: the quiet interior of the belt, so calm in appearance, remains connected to Earth through the slow whisper of thermal and gravitational drift. The narration widens now, holding in gentle focus the entire expanse between Mars and Jupiter. Countless fragments drift here. Without ever approaching a resonance, their orbits stable for the remainder of the Sun's lifetime. Others wander slowly into the faint pathways that carry them inward, though their departure represents only a tiny fraction of the belt's mass. Nothing in this process disrupts the belt's overall stillness. Dormant threats emerge only as natural consequences of orbital structure shaped by processes so slow they resemble a geological rhythm written in space. The section settles into a final quiet moment, acknowledging that the belt contains potential travelers destined for the inner solar system, yet the region remains tranquil, defined more by stillness than by hazard. The dormant threats lie not in violence, but in possibility shaped by forces that move with the softness of light and the patience of gravity across spans of time beyond human memory. The narration eases now into the long, slow memory of Earth's own encounters with wandering fragments, impacts that over geological ages have rewritten landscapes, altered climates, and left craters that endure as quiet records of stones born far beyond the world they eventually reached. In the calm tone of deep time, these impacts are neither dramatic events nor narrative peaks. They are simply part of the planet's ongoing interaction with its surroundings, shaped by the same gravitational architecture that guides every object in the solar system. The belt between Mars and Jupiter supplies only a fraction of these visitors, yet the fragments that do arrive carry within them histories that extend far longer than the landscapes they will one day reshape. A grounded, scientifically accepted fact settles gently. Earth has been impacted by asteroids originating from the main belt throughout its entire 4.5 billion year history. These impacts range from dust grains that burn up as meteors to meter-scale bodies that strike the atmosphere with brief flashes of light to kilometer-scale objects capable of altering global systems. The distribution of impact sizes reflects the size distribution within the belt, shaped by collisional evolution and long-term orbital drift. The craters left behind are not just scars, but geological chapters preserving evidence of events that took longer to unfold than any single moment could convey. Light drifts over one such crater, not a specific one, but the idea of a crater, a bowl carved into rock by energy, released in an instant after a journey lasting millions of years. The shockwave fractures the target rock, melted material pools and cools, airborne debris settles over hours or days, and then erosion takes over, slowly softening the crater rim over millions of years. A lesser-known detail emerges softly. Many terrestrial impact structures are hidden beneath sediment, vegetation, or ocean water. Some are identified only through subtle gravitational anomalies or magnetic signatures detected from satellites. These buried craters reveal impacts long forgotten, their structures preserved beneath layers of younger geology. A gentle mystery rises, persistent yet calm. How many ancient impacts remain undiscovered, erased by subduction, sedimentation, and tectonic recycling? Earth's dynamic crust offers few stable surfaces that persist over billions of years, meaning that the oldest impacts vanish over time, leaving incomplete records of early bombardment. The belt's fragments have shaped Earth more significantly than the surviving evidence shows, yet the narrative remains composed as these uncertainties drift softly across the story. Only took a fraction of a second for each impact to occur, only took a few hours for ejecta to settle, and only took the long, slow processes of erosion to erase the sharp details over millions of years. But it took billions of years of orbital drift for these fragments to reach Earth at all, making each crater the final quiet punctuation of a journey shaped by light, gravity, and time. the narration deepens into a contemplation of well-studied impacts. The Chicxulub crater, though famous, is not invoked for drama, but for its geological clarity. Its shape, multi-ring structure, and shocked minerals reveal the immense energies involved when kilometre-scale objects strike a planetary surface. Yet even Chicxulub represents only one event in a long continuum of impacts, each contributing to the subtle reshaping of continents and oceans. A soft irony emerges. The violence of the actual event contrasts with the calmness of the processes that led the asteroid toward Earth: thermal drift, resonance, gravitational nudges, forces so gentle they resemble the motion of dust in still air. Another quiet irony follows. The most dramatic geological features can arise from the most unhurried orbital evolution, and a third rests gently. The origins of these events lie in a region that itself appears tranquil. The narration moves to smaller impacts, the meter scale and tens of meters bodies that reach Earth far more frequently. When these enter the atmosphere, frictional heating ablates their surfaces, creating luminous trails. Most disintegrate high in the atmosphere, contributing dust and minerals to the stratosphere. Some reach the ground as meteorites, becoming physical samples of the asteroid belt's composition. These small arrivals are neither dangerous nor rare. They are part of a constant exchange of material between Earth and space. A soft analogy arises just as raindrops shape landscapes over long periods despite their modest size. The continual fall of space dust and micrometeorites contributes quietly to planetary chemistry, adding isotopes, minerals, and trace elements over billions of years. Shadows drift gently over the belt as the narration considers how families contribute to Earth's impact history. Some twin craters on Earth may reflect the breakup of binary asteroids delivered from the belt's families. Other craters show mineralogical signatures tying them to specific asteroid types. Carbonaceous chondrite fragments found in certain impact layers trace their origins to dark hydrated parent bodies. Metallic meteorites reveal past collisions that expose the cause of differentiated objects. Each crater, each meteorite becomes part of an extended geological conversation between Earth and the belt. A quiet scientific mystery lingers regarding the frequency of large impacts over Earth's history. While some estimates suggest periodic increases linked to asteroid family formation events, others argue for a more consistent long-term rate shaped by orbital mechanics. The uncertainties reflect the incompleteness of the crater record and the complexities of reconstructing orbital migration across billions of years. The narration stays calm within these uncertainties, observing them without attempting to resolve them. Light glances across the landscapes that impacts reshape. On Earth, craters fill with lakes, forests, or deserts, becoming habitats or geological landmarks. Some are ringed by uplifted rock layers that reveal deep structures otherwise hidden. Others become nearly invisible, softened by erosion, until only subtle curves remain. The slow processes that erase craters stand in gentle contrast to the suddenness of their formation, yet both belong to the same continuum of geological time, a continuum that mirrors the slow evolution of asteroid orbits. A soft observation emerges: impacts influence Earth, not only through energy, but through time. They contribute minerals to soils, alter the distribution of elements, and sometimes trigger volcanic activity by disturbing mantle structures. Over long intervals, these contributions shape the deep history of continents and oceans. Another observation follows: the belt's fragments are among the few direct participants in Earth's geological story that originate from beyond the Moon, and a third settles quietly. Each meteorite is a physical connection to processes unfolding far from Earth's surface, yet deeply intertwined, with its long-term evolution. The narration now moves gently to the concept of impact flux, the rate at which Earth encounters debris. This flux decreases over time as the solar system evolves, but resonances ensure that a steady trickle of new material continues to arrive. The belt's quiet machinery supplies this flux through slow dispersal, maintaining a long-term balance. Even as the number of large impacts declines, micrometeorites continue to fall daily, coating surfaces with traces of metals and minerals that once drifted on the far side of Mars. The atmosphere glows faintly with meteors each night, though most go unnoticed, contributing only brief flashes of light. The journey of these grains mirrors the journey of the larger body's slow drift, resonant entry, gravitational modification, and eventual interaction with Earth. Shadows sweep across the belt once more as the narration widens its focus to include Earth in the context of all planets. Every terrestrial world bears craters, each shaped by fragments that drifted from the main belt or beyond. Mars preserves mid-sized craters with remarkable clarity. Mercury is saturated with ancient scars. Even Venus, with its dense atmosphere and volcanic resurfacing, holds younger craters that mark past arrivals. These planetary surfaces reveal a broader truth. The entire inner solar system participates in the quiet migration of fragments from the belt, accepting impacts as part of their evolution. A final soft irony lingers. Impacts, though often labelled catastrophes, reflect not chaos, but the systematic evolution of matter across time. They are neither exceptions nor anomalies, but part of the solar system's natural rhythm, shaped by the same quiet forces guiding the belt. The section settles now into the calm realization that Earth's impact history forms a thread connecting the belt's ancient stones to the planet's geological and biological past. From dust that burns in the atmosphere to objects that dig craters kilometers wide, each arrival marks the final step in a journey, guided by light, gravity, and patience. These impacts do not disrupt the story but complete it, linking Earth to the belt through a shared history written across billions of years. The narration moves softly now into the long, unhurried evolution of the asteroid belt itself, a place neither fixed nor chaotic, but suspended in a state of gentle transformation that persists across billions of years. Here change unfurls with a slowness so profound that even geological time seems quick in comparison. The belt exists as a dynamic equilibrium, a region shaped by collisions, drift resonances, and gravitational rhythms that act continuously, though so gradually they resemble stillness. To observe this region is to observe time stretched thin, where each process contributes to the quiet reshaping of a population that has persisted since the earliest chapters of the solar system. A grounded scientific fact settles softly into view. The asteroid belt as it exists today represents only a tiny fraction of its original mass. Early models and meteorite evidence suggest that the primordial belt may have held enough material to form a planet several times the mass of Earth's moon, but Jupiter's gravity prevented accretion, stirring the region and scattering bodies before they could gather. Over billions of years, collisional grinding and gravitational interactions steadily reduced the mass, further removing fragments through resonances and delivering them toward the inner or outer solar system. Thus, the belt today is both a remnant and an ongoing process, less a fixed structure than a slowly evolving expression of ancient conditions. Light drifts across the stones, revealing textures that bear the imprint of both early formation and continued change. Some asteroids retain primitive materials unaltered since the solar nebula. Others preserve records of internal melting differentiation and catastrophic disruption. A lesser-known detail rises here. The belt-size distribution, the relative abundance of large, medium and small bodies, follows patterns that reflect both past collisions and present dispersal forces. The largest bodies resist fragmentation due to their gravity. Intermediate-sized bodies break apart more readily, and the smallest fragments are constantly created, dispersed or removed by radiation pressure. This shifting distribution tells a quiet story of balance between production and loss, between fragmentation and dispersal. Yet a gentle scientific mystery drifts alongside these observations. Precisely how the belt achieved its current distribution remains only partially understood. Models must account simultaneously for early high-velocity collisions, later slow-grinding varying thermal drift rates, resonance-driven losses, and the influence of past giant planet migration. Each model reproduces some features, but not all, suggesting that the belt's evolution contains complexities beyond present reconstructions. The mystery lies not in any dramatic unknown, but in the subtle interplay of processes operating across differing timescales. Only took the early solar system's chaotic instabilities to set the stage. Only took the migration of Jupiter and Saturn to stir the region deeply, and only took billions of years of consistent, gentle processes to produce the belt's present state, a quiet structure that still holds echoes of distant dynamical upheavals. The narration moves deeper into the changes that continue even now. Collisions remain a shaping force, though far less frequent than in the solar system's youth. New families form occasionally when a medium or large asteroid is disrupted, releasing fragments that spread slowly across orbital space. Over time, thermal drift elongates these families, mixing their members with other populations. Resonances remove some fragments, sending them inward as near-Earth objects. Others drift outward to join more distant populations, or eventually escape the belt entirely. Even the absence of events becomes meaningful. Long intervals without large collisions allow small asteroids to preserve surfaces many millions of years old, accumulating the faint signatures of space weathering. A soft analogy arises. The belt resembles a forest undergoing both steady leaf fall and slow regrowth. Trees collapse, saplings emerge, leaves decompose and enrich the soil, and the forest persists, no single moment defining it, but rather the continual flow of change across long periods. Here, stone takes the place of wood collisions, the place of decay and drift, the place of regrowth. Shadows glide over bodies that continue rotating with gentle regularity, their spins influenced by ancient impacts and recent thermal torques. Some tumble chaotically, others rotate steadily, their spin axes tracing patterns shaped by solar radiation. These rotations, though quiet, contribute to thermal drift, connecting the smallest motions to the slowest migrations. This interplay between rotation and orbital evolution gives the belt a subtle dynamism, even when individual bodies appear isolated and unmoving. A soft irony rests here. The apparent stillness of the belt is maintained by constant motion. The sense of quiet depends on continuous, almost imperceptible activity, and the persistence of its structure requires a steady exchange of fragments through invisible pathways. The narration shifts gently to the broader relationship between the belt and the planets. Jupiter acts as the primary sculptor, maintaining resonant boundaries and shaping long-term stability. Mars plays a smaller but meaningful role, affecting fragments near the inner edge. Saturn influences secular resonances that modify inclinations. The belt, though autonomous in appearance, is woven into the gravitational fabric of the planetary system. Each planet's orbit contributes a subtle rhythm that the belt responds to over millions of cycles. These interactions create long-term patterns, gaps carved by Jupiter's harmonics clusters formed by stable resonances, and dispersal zones where chaotic motion slowly spreads bodies apart. A gentle scientific question remains open. How stable is the belt over the remaining lifetime of the solar system? Models suggest that its current structure will persist, though, with slow, continual losses. Some fragments will drift inward, some will drift outward, some will collide with planets or each other. But the belt itself will remain recognizable, a long-lived, gently transforming region that outlasts continents, oceans, and perhaps civilizations. The narration now observes how dust generated by micrometeorite bombardment and collisions drifts inward under the pointing Robertson effect, slowly removing fine particles, while collisions replenish the supply. This ongoing cycle ensures that the belt always contains some level of dust, though never enough to resemble the imagined dense bands of science fiction. Instead, the dust forms a faint, nearly invisible haze that only reveals itself in scattered sunlight when viewed from specific angles. This dust, though small, contributes to the belt's long-term evolution by interacting with larger bodies, affecting surface chemistry and altering thermal properties. Shadows lengthen across the belt as the story widens to consider the energetic transitions between stable and unstable orbital zones. Some asteroids reside in long-lived pockets where resonant influences nearly cancel, allowing them to persist with minimal drift. Others wander into transitional spaces where slight perturbations accumulate, gradually altering their paths. The belt contains not only families but gradients of stability, age, composition, and evolutionary stage. These gradients make the belt a living record, not frozen, but evolving through slow processes that echo the early solar system. Another soft analogy emerges. The belt behaves like a coastline shaped by tides too slow for human senses to detect, yet powerful enough over millennia to define the contours of land and sea. Its changes are continuous and gentle, not dramatic, yet unmistakable when viewed across sufficient time. A final soft observation drifts into place. The belt remains neither stable nor unstable, but suspended in a state of gentle ongoing transformation. The stillness perceived from a distance conceals motion. The motion hides within it the persistence of old structures, and the persistence blends with slow change to create a region that holds both the memory of its origins and the inevitability of its evolution. The section settles now into a moment of quiet recognition. The asteroid belt, forever in motion, yet forever familiar, continues its slow reshaping, guided by forces that act with patience rather than urgency. It remains a place where ancient fragments drift through faint sunlight, carrying with them the long history of a system still unfolding. The narration drifts now into the quiet present of the asteroid belt, a place where stone continues its ancient motion through endless light, carrying histories that stretch back to the earliest moments of the solar system. Here nothing announces itself as new or old. Everything simply is suspended in an equilibrium shaped by gravity, sunlight collisions, and time. The belt persists as a diffuse congregation of worlds too small to become planets, too persistent to fade entirely, each fragment following a path determined billions of years ago and gently modified ever since. This final contemplative passage lingers not on origins or destinations, but on the enduring stillness that defines the region today. A grounded fact settles softly. The current asteroid belt contains hundreds of thousands of catalogued objects larger than 1 kilometer, and millions more too small to track, yet the total mass remains only a fraction of what it once was, far less than Earth's moon. This lightness is not a sign of depletion, but of balance. A balance between loss and replenishment, drift and collision, dispersal and gentle recollection. The belt's population evolves continuously but slowly maintaining its broad character even as individual fragments wander, fracture or depart. Light sweeps over the belt in a thin, continuous arc. It touches the carbon-rich bodies that absorb almost every photon, the stony asteroids that scatter faint glimmers, and the metallic fragments that respond with muted reflections. A lesser-known detail comes forward softly. The surfaces of many asteroids experience space, weathering a process that gradually darkens or reddens the uppermost grains due to solar wind, micrometeorite impacts and cosmic rays. Over time, these subtle alterations accumulate, changing spectral signatures and masking the true composition beneath. Thus, even when asteroids appear unchanged, their surfaces record the long, quiet interplay between radiation and dust. Yet a gentle scientific mystery lingers within this modern belt. How exactly small-scale processes, microfracturing, regolith migration, electrostatic dust lofting, unfold on low-gravity surfaces. Observations from spacecraft hint at unusual behaviors. Pebbles perch delicately on slopes steeper than those stable on Earth, dust migrating across surfaces, and boulders clustered in patterns unexplained by simple mechanics. These processes operate without haste, shaped by conditions far removed from terrestrial intuition. The belt holds these details softly, allowing room for discovery. Only took the sun's continuous radiance to maintain these rhythms. Only took Jupiter's steady gravitational presence to keep the belt from consolidating into a world. And only took billions of years for the region to arrive at this quiet middle age, where change remains constant yet almost imperceptible. The narration moves deeper into the belt's present-day architecture. Ceres continues its slow rotation, its bright spots of briny deposits reflecting faintly into space. Vesta still carries the enormous scar of its ancient southern impact basin. Pallas drifts at a steep inclination far above the belt's midplane. Countless smaller bodies rotate irregularly, shedding tiny grains of dust. Each of these worlds experiences its own internal and external transformations, none fast, none loud. Even Ceres' potential subsurface brines inferred from spacecraft data exist not as active oceans, but as localized, slowly evolving reservoirs shaped by the residual heat and chemical gradients. A soft analogy arises. The belt resembles an ancient library whose volumes remain scattered across a vast floor, each book weathered by time but still bearing traces of the stories within. Nothing rearranges the library abruptly. Instead, the position of each volume shifts only when time and physics coax it gently elsewhere. These shifts, though subtle, ensure that the library remains alive with movement even as it appears undisturbed. Shadows stretch across the belt now, though the shadows here are not cast onto surfaces, but into statistical space, into pockets where few bodies reside due to resonances, and into clusters where fragments gather due to shared origins. These shadows and clusters coexist without tension, forming a structure that appears both patterned and diffuse. The narration observes that the belt is neither uniform nor chaotic, but textured by ancient forces still at work. A soft irony drifts in the belt's stillness, requires constant motion. Its identity as a place of fragments relies on processes that slowly erase fragments, and its appearance of emptiness conceals vast histories contained within each drifting stone. The narration shifts to the faint dust that fills the spaces between larger bodies. This dust, continually replenished and continually lost, forms a delicate halo known as the zodiacal cloud. Some of it spirals inward to the sun, some is pushed outward by radiation pressure. It glows faintly in the early morning and evening skies of Earth as zodiacal light. Though barely visible, this glow is one of the belt's quietest gifts, a subtle illumination that carries across dozens of millions of kilometers, reminding Earth that the belt is not remote but part of the planetary environment. A gentle scientific mystery follows how the smallest dust grains survive for as long as they do, given the forces acting upon them. Models predict rapid removal, yet observations show persistent populations of specific grain sizes. This persistence hints at processes within the belt, continued collisions, electrostatic effects, perhaps contributions from comets that maintain the dust in delicate equilibrium. These mysteries remain soft and unresolved, not gaps in understanding, but invitations to contemplate the fine interplay of forces shaping the smallest participants in the belt's ongoing story. The narration expands further, considering how spacecraft have revealed the belt's present condition. Missions like Dawn have shown the unexpected complexity of Ceres and Vesta cryovolcanic activity in the past, differentiated interiors, bright salt deposits, large-scale slopes and ridges that challenge assumptions about low gravity. Smaller missions and telescopic surveys uncover binary asteroids, contact binaries and bodies whose shapes defy simple classification. Each discovery adds quiet nuance to the portrait of a region that from afar appears simple and uniform. A soft observation arises. The belt's richness lies not in spectacle but in subtleties. Not in dramatic events, but in the fine details accumulated across billions of years. Another observation follows stability and change coexist here, without contradiction, shaping a region that evolves slowly yet remains recognizable across vast scales of time. And a final observation settles gently. The belt's present is inseparable from its past and future, a continuum of quiet motion expressed through stone dust, sunlight and gravity. Shadows glide once more across the belt as the section approaches its resting point. The stones continue drifting, turning and absorbing light. The dust continues spiraling gently inward. Resonances continue carving gaps and guiding fragments. Everything continues without hurry, without pause, without intention. The belt remains what it has always been, a domain of ancient fragments bathed in endless sunlight, carrying histories that extend far beyond the fleeting present. In this enduring stillness, the asteroid belt exists as both archive and ongoing process, a quiet region shaped by forces that act with patience measured not in centuries or millennia, but in the long breath of cosmic time.